parameterization of the tangent line to that point. Okay. Ask yourself at the end of a question where you're asked to find the parameterization for a tangent line, do I actually have the parameterization of a line? If you don't, it's not what you're, I mean, you've forgot to plug in the time, right? Okay, most likely. All right, so let me introduce the next order of business, which is understanding a little bit about the basic geometry of curves. Let me just set up the problem for you. Here's our ultimate goal. Well, here, something you guys probably thought about in high school some, is if I have this triangle here, right? And if I have this triangle here, are these the same triangle? I mean, up to the limits of my artistry, if, you know, if these are equilateral triangles, right? If these are equilateral triangles, and if you also know that the length of one of the sides is the same, right? If this has side length 2 and this side length is 2, I think we would all agree that geometrically these are the same triangle, right? What do we really mean by that, though? We really mean that we can take one triangle and through sort of a standard motion in physical space move it to the other one, right? Like I could pick this triangle up, right? And I can move it over here, translate it like so, and then turn it around. Oh, my hand doesn't do that, but you could rotate it and overlay it exactly on top of the other triangle, right? And so you can start asking the question, when are two shapes the same, right? So like if the edges have the same length and they have the same kind of like same interior angle and the relation of different interior angles is the same, we put all this together, they should be the same polygonal shape, right? Like you could tell whether or not two things with four sides were the same by measuring the length of each four sides, making sure that they're at the same angle relative to the interior angles. You could figure out whether or not you could translate one to the other and rotate to overlay, right? Such things are related by what are called, this thing I'm describing is what's called a rigid motion. It's a combination of a translation and a rotation. How would you do that for curves? How do you tell, right? How do you tell if this thing and this thing are the same curve? I mean, how do you know if they're the same shape or not? Is there some method for doing this? That's the question of the classical differential geometry of curves, is deciding when are two curves actually really the same shape. Turns out that we can answer that question for a pretty decent set of curves by saying, you know what, they're the same shape if you can like pick a point, you know? If you can pick a point on each one of them and the arclength function like behaves the same. And also if they have the same, with respect to that arclength, if they have the same curvature and torsion. So curvature describes how curvy it is, and the torsion describes the tendency of the curve to lift off a plane. So like a circle has zero torsion, whereas a helix has constant torsion because it's always like lifting up off whatever plane the motion is infinitesimally. A line has zero curvature. A circle has constant curvature, right? So these are things we'd like to make precise because that's kind of exciting. We can extend this notion of high school geometry congruence to arbitrary curves by just saying, well, if I can calculate the curvature and torsion and they match up, despite the fact that they might look kind of different depending on your viewpoint, they're actually the same curve. Besides that, this is a way you could set up moving coordinate systems, which might be interesting from like a mechanical engineering perspective, right? So long story short, here's the deal. We take a path, we pick a point, and what we're going to define is the tangent vector like that. The tangent vector is going to be, you know what it is? It's v hat. All right? And to keep things unambiguous, we'll start by taking a unit speed parameterization for the curve. So if we have a unit speed parameterization for the curve, what is the velocity for a unit speed curve? So velocity for path, generally speaking, as we've talked about, it's the speed times v hat, right? But what is this if we're unit speed? It's just v hat, right, for unit speed. So for a unit speed curve, the unit tangent is just in the direction of the velocity, right? And then the next thing we'll define is the so-called normal vector. The normal vector will point towards the center and of what's called the osculating circle. The osculating circle, if you can fit a circle like this, the osculating circle will fit. It's osculating is like a Greek for kissing. My children will be like, ew. Sorry. So it's the circle which just kisses the curve at the point of tangency, like that. It shares the perpendicular to the diagonal of the curve that goes through that point of tangency is matching the tangent line to the curve, in the sense I just showed you how to calculate. So this is called the unit, and we also insist this be a normal vector, n for normal. This is the Frenet normal. It points towards the interior of the osculating circle. And we're interested in creating a frame of vectors. That's a right-handed triple. 3 vectors which are mutually perpendicular, which means they enjoy all the rights and privileges like you've seen in your homework. You take dot products with respect to this nice orthonormal frame. It's easy to pick off components, right? Like the C1, C2, C3 problem. How do you get the B? I think you guys already know. How do you get the third vector which is perpendicular to these two and also has unit length? Cross product, right. Now, I didn't guarantee, and I can't draw that worth a hoot, but something like that, B. Did I do it right? I don't know. I better use my right hand rule, right? T, crossed in there, it's kind of into the board. I don't know. How do you draw into the board? I tell you what, I'll do the circle deal. What do we do? Circle cross or circle dot? Circle cross, right. So there's your B. That's the so-called binormal. And I don't usually draw a vector on it. I usually just leave B for binormal. N is normal. The T is the tangent. So you have the tangent, the normal, and the binormal. All 3 of these together form what's called the Frenet frame. All right? Excuse me. I think I have a picture of these for you guys. Oh, but well, anyway, if you know the website, right? If you look at the course website, I have that annoying GIF in the background. If you look at it, what that is the Frenet frame as it appears along a curve. And the Frenet frame like follows the curve as you go. It's a winding, it's a local coordinate system. It gives you a setup for a local coordinate system each point. Anyway, I'll shut up. Thanks guys, see you tomorrow.